Welcome to another class, another week where we meet here on YouTube to bring you practical and theoretical tips that will help you on your journey to become a climate technician. That is, to learn how to repair any electronic board in the climate control segment and even make 10,000 REAs per month with this type of service, repairing electronic boards. I'm Lawhander, a climatronic engineer. Today we're giving a lesson on the LG air conditioner error CH23. The error code CH23 on LG air conditioning units. CH23 on LG air conditioning units, if you refer to the manual, it indicates DC, specifically low voltage DC. Oh, it really hurts the soul, doesn't it, man? It really hurts when you see the manual talking about voltage. Then the translator ultimately translated it accurately for me. CH23, low voltage direct current. And beyond merely informing you which component to replace, my classes, as the more seasoned individuals are aware. I don't particularly enjoy bringing you here merely to say, oh, replace this component and it will function properly. I aim to provide you with the reasoning process behind the defect resolution. Eventually, you ought to move beyond the initial category inquiries. When you encounter a defect, you want to know which component you will use to resolve it. This is a first category question. It's a superficial question that anyone would ask. Now let's think, what causes this defect? What could cause the CH23 error? Low DC voltage error. DC voltage is the voltage that resides in the power capacitors. It is the direct current voltage. It is the 310 volts that persist within the power capacitor. What might lead to this voltage diminishing? What could potentially cause this DC voltage error to occur? This is what you should ask yourself, not which component to replace, because otherwise you will never become a professional in board repair. If you only focus on replacing parts, you will just be a parts replacer. And it is perfectly acceptable to be at the starting point of your journey, to be the one who swaps parts. We all begin as parts swappers at the onset of our journey. What I find problematic is remaining a parts swapper throughout your entire life. And when you repair your first board and make money from it, you've already seen that it's possible to make money from board repair. You've seen it, you already have the clarity that you can make money from board repair. At this point in time, when you have not yet completed a repair, you do not possess that understanding. Once you perform a repair, there is nothing beyond that. There is nothing beyond that. How do you see this thing? You've repaired it once. You have already generated income through the board repair. Do you comprehend? And there is no service that is more financially rewarding within the air conditioning sector than the board repair. The margins are absolutely absurd. I am not aware of anything more financially rewarding within the sector than the repair of boards. However, the topic at hand isn't about profitability, correct? So you need to ask about the defect. Let's think here. Let's think, I'm going to the board now, okay? To show you which circuit you should analyze. But first, let's think here. I have the boards here on the bench. Let's think here. Let's interpret. Apply the method I teach my students, the three-step method, the OET method, the method of thinking about defects. Listen, examine, and treat. Listen, examine, and treat. Let's contemplate this for a moment. Come on, let's conduct an analysis. Accompany me in this line of thinking. The issue at hand is low direct current tension or low direct current voltage. Voltage can be quite harmful, can't it, my friend? Voltage is not correct, all right, everyone? Voltage in English is accurate. It's voltage. When you translate voltage into Portuguese, it becomes tensão, all right? It's not voltage because we've already adapted the English to Portuguese, right? It's like amperage. We've already adapted it, right? It's current. It's similar to bypass, which involves bypassing or circumventing the circuit. Bypassing is the version in Portuguese, while bypass is the term in English. When there exists an accurate cognate replacement, we proceed and utilize the corresponding equivalent replacement, in fact. We don't have it there, use the word in English. Anyway, the low DC voltage. First, what is the DC voltage? The direct current voltage is 310 volts, all right? The direct current voltage is 310 volts. Great, all right, I comprehend. There are multiple voltages on the board. AC voltage 220V, DC voltage 310V, 15V, 12V, and 5V. Which voltage does this error refer to? The direct current voltage of the power capacitor, which is a high direct current, is the only one that the board measures. This is the reason why it is referred to as high direct current voltage. The board measures both AC and DC voltage. If it mentions a DC voltage error, and the only DC voltage the board measures is the 310 DC voltage. So take notes, because as I teach you here, I'll be sharing a lot of knowledge throughout the lesson. So this is one of them. When it comes to reading in DC voltage, the board only reads the DC voltage at 310 volts. It doesn't read other DC voltage, okay? If you didn't know, now you do. Note this, the board only reads DC voltage. There are two possibilities for this error. Let's create a line of reasoning here. And first, I listened. First, the OET method is to listen, examine, and treat. So I attentively listened. I discerned the board. I perceived the error. Now I shall formulate hypotheses. Our work at the bench is to formulate hypotheses and test hypotheses. Formulate hypotheses and test hypotheses. The more experience you have, the more accurate your hypothesis will be. The more assertive your hypothesis will be. The less experience you have, the more you'll wander. The more you'll get lost in thought. Because you will think of random things that make no sense. Everything is a micro. And that's how it works in the beginning. It's okay, it's the beginning. As I mentioned, you start by changing feet. Component exchanger. We have this journey. Me more than ever. More than 2,000 people have already been trained there. And counting, right? Almost 3,000 people already trained. Trained with efficiency, with productivity, with self-repair. Returning, I will raise hypotheses. And I will raise the hypotheses to later check the hypotheses. And there will be classes here, folks, where I will present the defect that I corrected, which was fixed here at my company. And there will be classes where I will provide a more detailed analysis of the error. In this lesson, I'll mix both. What I'll share here, I've encountered this defect a few times. And it's for you to also think about the defect itself, the logic of the problem. CH23 DC link error. The DC link exclusively possesses a DC link with a voltage level of 310 volts, thus presenting me with two potential scenarios. Either the 310 voltage is absent or the 310 voltage is missing, or if it hasn't been charged, then the board is functioning correctly and it will indicate the accurate error. Or it's low, right? If not, it wouldn't show an error. First thing, what do you mean, Lawhander? Because if there's no DC voltage, no voltage on the board, it won't even turn on. If it won't turn on, it won't show an error on the condenser. And it would result in a communication error within the evaporator unit. Is everything clear up to this point? So it is powering on, but the voltage level is insufficient. It needs to have 310V, 300V, 290V, 280V. Many machines can handle up to 260V. The LG, if I ask it to be passive, can handle a low voltage like that. However, if the voltage decreases to 250 volts, for instance, 240 volts, or even 180 volts, the circuit board will activate and continue to display the error message. And it will indeed be an error appropriately, correct? In that case, it could be a PTC in the circuit. It could be a PTC heating up, lowering the voltage. It could be that the PTC relay did not remove the PTC from the circuit. It is possible that the power capacitor is malfunctioning. There could be several potential issues, correct? I will show you on the board what you will analyze when it's this kind of thing. I'll show you in a moment. Alternatively, it might be necessary for you to pay closer attention. Based on my experience, the majority of situations are similar to this. Please pay attention. There is 310 volts, correct? That's right. However, the machine halts and displays an error causing the connection to fail. It is the direct current voltage. The voltage level for the board is insufficient. When that particular situation occurs, which is the second hypothesis I am presenting here with you, at that moment, you will carefully examine the circuit that is responsible for reading the voltage. It makes perfect sense, everyone. If the circuit board indeed has 310 volts and you have measured it using your multimeter, observing 310 volts, it is a substantial and powerful capacitor. It possesses 310 volts, and yet the circuit board indicates it does not. It must be interpreting it incorrectly. Do you comprehend? There is voltage. You saw the voltage. You measured the voltage, and the board is telling you there isn't any. Therefore, it is being misled. It is interpreting the data inaccurately. In order to determine whether the voltage is high or low, it must accurately read the voltage. For the board to say voltage is high or low, it must read the voltage. Does it add up? For the board to say that the voltage is high or low, it has to read the voltage. So it will read the voltage, and it will read it incorrectly. If it reads incorrectly, it will give the error incorrectly. She'll have two hypotheses. These are common in such cases, right? But I have the machine here. It starts the compressor and should lower the link. It should hit 23 and start the compressor. When the compressor starts, the voltage drops and the error occurs correctly. You go there to measure when the compressor starts, the voltage will drop. You'll see it dropping when the compressor starts, then the error occurred correctly. Understand this. Stop this bad habit of the machine reverses, there's an error, it's the board. It showed an error. It's the board. It showed an error. It's the board. Not always, folks, is the error wrong. What do you mean, Lawhander? The error showed a decoupling error, low voltage. Or it might be a direct current voltage error indicating low direct current voltage. Occasionally, it can indeed be low. Proceed and measure it. If it is low, the board is correct. Sometimes the compressor starts, draws current, trips the PTC, or sometimes the neutral is grounded at the client's house, the machine starts, the voltage drops, and it causes the error. Last week I had a disc with me and we discussed that idea. And because his client's board had the neutral grounded attention, it would drop when starting the compressor, but it didn't give a DC link error, it gave a communication error. He found it odd. Shouldn't it have given a DC link error? It should have. However, it resulted in a communication error, which is already the primary priority of the board. Consequently, it turned out that the board did not. It prioritized the communication error over the voltage drop error. So let's consider these two hypotheses. Are these clear to you, class? Does this logic make sense to you? Did that approach to considering the defect make logical sense to you? That's precisely what you need to cultivate within yourself. Develop that capability internally. However, I am a mechanic. I am present to acquire knowledge on how to mend the circuit board or to receive any advice you might offer me. Therefore, consider this suggestion on examining the machinery. As during my time as a mechanic, which was in the year 2021, I am now transitioning into a role as a corrective mechanic at my current organization. I set up the operation and went to the field. I worked with my dad, installing and cleaning machines, but I was young, so I didn't pay much attention to those things. I didn't have the mindset I have now. When I returned to my company for mechanics, I went into the field and applied the same methodology to find mechanical defects, man. I've always liked working with defects because the ones who make the most money in the market are those who work with defects. Who makes the most money in the market is the one who works with defects, right? Or big projects, large construction companies and such. But the best, individually speaking, the best way to apply your knowledge is by fixing defects. So I've always liked defects. They've always attracted me a lot. And then correcting a mechanical defect adheres to the same reasoning. Identify the issue, develop a hypothesis, and then verify the hypothesis. OET, pay attention to the error, thoroughly examine the malfunctioning circuit, and address the specific circuit where you identify the defect. Conduct a search, and then perform a test. It applies to electronics, it applies to any type of equipment, right? Dakin significantly lowers the voltage, correct? Any equipment that has passive PFC, the voltage drops considerably. That's why there are machines that work with 160, 180. I've seen machines working with that. T-Spawn, for example, operates with very low voltage. At a high compressor rotation, they accept it because it has low PFC or passive PFC. But that's another topic, right? You're waiting for Oswaldo there, who knows about the circuit. All right, let's go to the bench. I'll show you the circuits, the logic, and which circuits you'll analyze. I have two LGs here on the bench. I'll explain with one and then with the other. They are the most common on the market. A significant detail prior to proceeding to the workbench is that the LG error is indicated by the blinking of the LEDs. For those who are not familiar, this is how you will read the LG error. The LG error is read in the following manner. Whether it is in the condenser unit, the evaporator unit, or the condenser unit. In the evaporator, there will be two LEDs, where one LED represents units and the other represents tens. For example, if the tens LED blinks twice and the units LED blinks once, it indicates error 21. 2 blinks for 20, 1 blink for 1. It blinked. This one is the CH. There is a CH indicator in the front, correct? This particular one is CH23, which means the tens LED will blink twice and the units LED will blink 3 times on the evaporator's LED indicators. If there is no blinking on the evaporator, it remains in its normal state with the LED illuminated, indicating normal operation. In such a case, you should proceed to the condenser unit where it will have an LED and this CH23 will blink twice, followed by 3 times, and then pause for an extended duration. Blinks 2 times or blinks 3 times, correct? It is tens and units, so it will blink 2 times representing 20, then pause, blink 3 times representing 3, correct, 23, and then a longer pause. Then it starts again, 2 blinks, pause, 1, 2, 3, longer pause, 2 blinks. Therefore, analyze the error and the lag of the condenser as well because it will assist you. Where do you find so many error codes? Because if it's an error code, you're going to work against yourself. If the machine says it's hurting, it tells you where it's hurting. It tells you what it's feeling. Why would you disregard it? So go ahead and consider what it tells you. Listen to it. That's why listening is the first step of the method. Listen to it. All right, so I heard the error. CH23. CH23. Then I go to the error codes merge, which is the WhatsApp I created for you, the AI I created for you. You go there and ask her, what does it mean? Sometimes it's unstable, but it's free. If you're patient, it starts working again. You send a message asking, what does it mean? It means this, this, and this. Then he will tell you what it means and you will analyze it based on my knowledge about board repair. The AI of the master of error codes. By the way, I am planning to modify it and I intend to enhance it in the near future. I will be working on it shortly. Does that sound good? Let's head to the workbench. So, do you already know how the LG error code came about? It's clear. Let's get started here. I'll begin with this smaller board of the dual inverter, recognized as, indeed, the dual inverter. LG dual, correct? Observe this small face here, all right? Let's proceed. This is the capacitor that requires attention. This board, you usually access it here, right? Flipped. So this part here, the voltage needs to be on this capacitor. You will measure as the voltage scale drops. In this situation, it will not provide any reading. Carefully, you should measure it, and it ought to display values such as 310, 300, 290, or 280. It should be within the range of 280 to 310. Operate within this specified range, all right? Measured here, there's no voltage, or it's low, as I mentioned. If it's not there, it won't cause this error. It has to be low. If it's low, it will cause the error, and the error is correct. In this case, what could it be? I would analyze I would check if this component that's heating up, which is the PTC, is indeed heating up. If it is heating up, it's because this relay here did not remove this PTC from the circuit. This relay did not activate. If it did activate, it might be faulty. It could be the relay, or it could be the circuit that activates the relay, all right? It could be the relay or the circuit that activates the relay if the PTC is heating up, or if 220 is dropping, I check if 220 is dropping. If 220 is not dropping, it's not low, therefore the capacitor's voltage should be high. If there is 209 here, 210, 215, the capacitor should have good voltage. If it doesn't, it's this little circuit here, okay? Generally, the problem will be with it, the wonder. If it's that, as I mentioned, it's either the relay activation, or the PTC. Generally, it does not typically appeal. It is usually the activation of the relay, the circuit that is responsible for activating the relay, which contains the relay coils and the relay contact. You simply need to follow the coils here, and you will observe the circuit that activates it. All right, everything is good, understood. What we are going to do here is conduct an analysis of this circuit. If it is not, and if there is voltage present in the capacitor, but still the board is displaying a communication error, that is precisely where I intended to delve more deeply into today's lesson. Honestly, this power circuit here is quite straightforward. Here's a relay and a PTC. It heated up. Check the relay and its activation circuit. See if there are 12V on the relay coil. How do you measure 12V on it? Set the DC voltage scale and place one probe here, another there. Then check for 12 volts. If 12 volts are present, this relay should activate. Then check if it's activated here. I check the voltage here, AC, right? I see if 220 is reaching the bridge. Check 220, check 310. If there is 220 and not 310, it's below 310, the issue is around here. If there is no 220, it's also below 220, the issue is in the network. It's a grounding that is on the neutral connected, which is wrong. It pulled the grounding and it wasn't the neutral. Anyway, it's an issue in the electrical system. Lawhander, I saw that there are 310V here. Tell me that there are 310V, but the board says it's with DC link. What are you going to do? You will take this board, flip it over here, and inspect it, searching for the positive. Initially, the capacitor has a specific marking. This marking here signifies the negative side of the capacitor. So the other side is positive. There are two pins, right? So this one is the negative. When I turn the board here, this is the negative and this is the positive. So what am I going to take? The positive trace. Look at the positive trace here, man. It is quite an extensive trace, see? I will take the positive traces and search for any location where traces are diverging, right? For some type of reading, okay? Some type of reading. And subsequently, I arrive here, observe. I'm back here, look, pay close attention. This is the path, see? This is the path right here, see? I have a jumper. I'll even show you what a jumper is. I'll put its continuity here. A jumper from here to there. There's a jumper. It showed 0 and 1. It's showing here to see. It is displaying here. I will simply adjust the inclination on my multimeter. Finished. Display. Excellent. It will be located here. This particular one arrives here. It arrives positively from the IPM. It is not located here. It is not located here, correct? There is a capacitor located here. However, there's an additional output present here. Do you see it? There is a jumper that extends from this point to that point, correct? There is a jumper extending from this point to that point, and then I will proceed to follow the pathway here. Do you see it? I followed the pathway here. Do you see it? A jumper arrives here, and this one proceeds to the transformer coil. All right, the transformer coil, which is what exactly? The transformer coil, specifically the primary winding of the transformer, is responsible for taking the electrical voltage from the capacitor in order to generate the primary winding of the transformer. This is a fundamental standard of the switched mode power supply, but additionally the circuit will diverge at this point. Everything in this section is part of the power supply circuit, and there is a resistor located here that connects to another resistor, which then leads to yet another resistor. In this location, there is a capacitor, correct? There is a capacitor that ought to be connected to the ground GND, this particular capacitor, correct? Certainly. Forget the capacitor. There is a resistor here, it has to go over here. So there is one resistor, two resistors, three resistors, and the middle pin of this resistor has a trace that comes here to a path over here. Let me see if I can find it here. It descends along a certain path here, reaches this point, then proceeds to this location and eventually arrives here. It traverses through a resistor and continues onward to the microcontroller. From the resistor to the microcontroller, it measures 0 ohms. I'll apply more pressure here for you to observe, utilizing it for logical purposes. Positive connection here, positive, and pass a jumper wire here. Here there's a resistor that connects from here to here. This point has another resistor that comes here. Here there's another resistor that comes here. This is GND, okay? Then this capacitor here, GND. So at this point, it no longer performs analysis, but I observe that precisely in this central area, if you examine closely right here, allow me to adjust the focus here, will it adjust? Unfortunately, it will not. Look, here, a trace comes out like this. This is the route I pursued. You observe it arrives here at the eye and it might become obscured in your perspective, but it proceeds over here to this specific point, to this particular pin. This pin here possesses a resistor extending from this location to that, and from there there's a capacitor leading to the GND, and it continues to the microcontroller. The microcontroller is shorted if this board here is a scrap board with the microcontroller shorted, but the logic here pertains to this circuit. What is the issue that might arise in this circuit that could result in a reading error? In the circuit that I have just demonstrated to you, these components are the resistors located here. These components are the resistors positioned here. These particular resistors, please continue observing here. It will be specifically this particular resistor, this specific resistor, and this particular resistor, correct? It is these three resistors. They are going to transmit a reading, a sample of the electrical voltage to the microcontroller. I observe the route I followed to reach the microcontroller, so it takes 310 volts and reduces this voltage across two high resistance resistors. These two resistors will have a sample, for instance, let's say it's 310 volts. When it's 310 volts here, there will be 3.1 volts here. Let's assume it decreases by 100 times, correct? It's 100 times smaller, so I have 310 volts here, and here it will be 3.1, for instance. It's merely an example. I don't know the precise value. I would need to verify the voltage map to determine this, but there will be a voltage sample here. This voltage sample will reach the microcontroller, and when the microcontroller reads this voltage, it will recognize that this voltage is present. Since this voltage is present, the board will read the voltage that is here proportionally. Do you agree with me? If any of these registers here change, especially these two related to the reading, if any of them change, pay attention. If any of them change, the reading will arrive incorrectly at the microcontroller. So, when you take a circuit board equipped with MD Clink, CH23, LG, and you guide me and there is an electrical voltage present, it is because the voltage reading circuit is incorrect, correct? The intention behind the reading circuit is incorrect. Therefore, it is reading inaccurately. Typically, this is either because of another open island, a cold solder joint, or generally an altered resistor. As they are measuring resistors, these resistors must provide the accurate value. They must deliver an exact value precisely on target. How often have I faced a defect? The issue was replacing the resistor. So I ask you, repairing a board like this cost me 450 Rs. I repair a circuit board of this type for approximately 450 reais. The cost ranges between 350 and 450 reais. A valve like this costs less than 50 cents, 10 cents. Which service within the air conditioning industry yields the highest profit margin? Could you elaborate on the service that boasts the highest margin? Please provide some insights about it. There isn't one, man. I've researched it. I'm immersed in this market. That's why I play the board repair game. There are no identical images. So folks, if it's low voltage, it's that first path. If there's voltage, the error will be in the reading. Where? On the other board? On the other board indeed, of course. Let's move on to another board here, to another LG model. Now, you already know the signal. I'll be quicker now. You know the logic, right? Measure the voltage is low, the average is 220. It's 220 it is, the voltage is low. The problem will be with the PTC. The PTC will be here, see? If it is heating up, it could be the relay that hasn't been removed from the circuit. Check this relay and the circuit that activates the relay. Look here, relay, this is the relay, this is the relay when we turn it. This pin too, when you turn the board, sometimes I get lost too. Look, there's a relay connector here, and here are the two pins of the relay coil. See if there are 212 volts at the relay and check if it closed the contact, okay? Now, but pay attention to the capacitor, and now what do? Flip the board again. Let's proceed. This particular one is larger, correct? The capacitor is located here, and I'm searching for the positive terminal. The positive terminal is this one, isn't it? I will examine along the positive track to determine what interprets this particular signal. Here is a capacitor, here is the transformer coil, here is another capacitor, and here is the notion of a resistor. But there exists a resistor, however. It is the resistor of the primary circuit. Therefore, the signal does not proceed in this direction. It is not in this direction. I shall proceed in this direction. Here is a jumper. That comes from the builder bridge. It's not here. There's a jumper right here. See? Oops! It's not even a jumper. It's already a resistor. R-O-M-Y. There's a resistor here. There's another resistor here. This trace, see? It comes here if I follow it. It arrives to make contact here, proceeds over to this location, and at this point it already inquires, which is not precisely what I desire. It continues well over here, and the HD arrives here, correct? Please come over here and observe closely. If you notice that it's providing a reading, take a look at my multimeter situated here in the corner. I'll move it from this resistor over here to this other resistor. It's because you might not be able to see it clearly in the video, but with a bit of patience, if we trace the path, you can see it clearly. This trace reaches the resistor and the opposite side of the resistor is coming. Let me verify here to see if it connects to the microcontroller. Look here, it indeed connects to the microcontroller on the opposite side of the resistor. So there's the resistor and here's the capacitor. You continue tracing with your finger, providing a reference, and then the other side of the resistor connects to the microcontroller. Consequently, it reduces the voltage through these two resistors right here. See? Here they are, look. These two resistors, look. Take the positive, which is the negative, okay? It takes the positive here on this side. Drops the voltage, comes to this resistor here, passes through the resistor, and goes over here. Look, there's the voltage and the reading is off. The resistor might have changed. There could be a cold solder joint, or this circuit here is altered. It's either a cold solder joint, an open trace, or changed resistance. Usually it's changed resistance. Clear, class? We're in this together. Talk too much.